The next example we are going to look at is that of the action of a distributed load on a cantilever beam. Still, the question requires us to find the displacement at point A and then at point C. Starting with the point A, we say that our first step is to draw the bending moment diagrams. So if let's say we begin by drawing the bending moment diagram of the action of the original force, we'll be having such a diagram here. Like instead of a straight line this time, we do have a curved line. So here the magnitude as known to us would be a half QL squared. Then the next thing, we come and draw the bending moment diagram due to the action of the unit force at a point whose displacement is required. For this case is point A, so we add there a force Fp is equal to 1. So that one there, we also saw that the bending moment diagram would just be exactly of this nature. So the magnitude here would be equal to L. So with all those known, the next thing we do, we come and find the A. We say that A is calculated from the bending moment diagram of the original loading. So before we think about all its calculation, we should ask ourselves, is the shape that I'm having part of the basic shapes? Yeah, from our observation we can see that such a curve is part of it, and then even this one here is part of it. Then besides that, it is all continuous. It's a continuous shape under the same range, so we've got no need of dividing the shape at any point. So the area of this shape here, we saw that is given by 1 over 3 BH. So in this case here, our area would be equal to 1 over 3 times QL squared, then times L. This one gives us, QL squared over 2. This one gives us 1 over 6 QL cubed. Then we come and find the Y. We say that the center of this shape is at this point here, like a fourth from this point up to here. So we come and draw that imaginary line, and then this one here would be our Y. So from the idea of similar triangles, this part here would be a 1 over 4. 1 over 4 means that this 1 over 4L, then this side here would be a 3 over 4L. So when you use similar triangles here, we shall find that our Y would be equal to 3 over 4L. Therefore, our delta A would be given by 1 over EI into AY, into summation of AY. So in this case, this would be equal to 1 over EI, then into this would be 1 over 6 QL cubed plus 3 over 4L. This one gives us delta A equaling to 1 over 8, sorry, this is a times, not a plus, 1 over 8 EI QL power 4. Then next, come and look at the displacement at point what? At point C. So we first begin by drawing the bending moment diagrams. So we begin by that one of the original loading of the structure of this nature here. It would be that kind of a curve, and then at this point here we shall be having a magnitude of what? A magnitude of 1 over 2 QL squared. Then the next one here, we shall be having the unit force acting at a point C, because it is the point whose displacement is required. Then the bending moment diagram would be something of this nature here. This would be a half of L. So we try to look at the kind of shapes that we are having again. We discover that our shapes are not continuous over the same range. Like this graph here ends off at this point, and then it changes shape, but then for the sake of this one, it continues as a smooth curve. So meaning that we are supposed to divide the shape from this point here from the point of discontinuity, which is this one here. Then after we do that, we come and try to form basic. Try to come and see whether we have basic shapes. So for the sake of the action of the unit force, we know that this is a basic shape, but then for the sake of the action of the original loading, now initially we had a basic shape, but now after dividing our shape from this point, it is no longer a basic shape. So we've got to find ways of manipulating it. But right from observation is that when you look at this shape here, its y would be equal to a 0. So we won't concentrate onto this side, we shall just concentrate onto this side here. So for the sake of such a graph, the best way to operate is by joining a line at this point here, like so as you come and form a semicircle here like that. Then besides that semicircle here, we discover that we've also formed a trapezium here. So the trapezium, we divide it into what? We divide it into two to form a rectangle and a triangle. So now we need to come and find the moment at this point here. So how do we find that? We come and consider the same type of beam, but now we just draw it to the length of a half L. And then under the same action of the same load, so to find our moment at the height of the rectangle, if this is point A and this is B, the moment at A would be equal to, if this is of magnitude Q, here we shall be having a concentration of what? A concentration of QL over 2. So therefore our moment would be equal to a half of L over 2, which would be L over 4, then times Q L squared, which gives us 1 over 8 Q L squared. So therefore at this point here we have a moment of 1 over 8 Q L squared, like that. So after we found that, we come and label our areas. This should be area 1. I'm calling this one area 2, like this triangle here, like this. And then lastly this semicircle here up, I'm calling it area 3. We come and begin our manipulation. So beginning with our area 1, we know that our area would be given by the length times the height. Yeah, for the sake of our length is given by L over 2, then times our height. Our height is 1 over 8 Q L squared. This gives us 1 over 16 QL cubed. Then our y1, we shall take it from the center here, then you come and pull it downwards. Then since like this is L over 2, this will be L over 4. So even this side here would be L over 4. We come and use similar triangles and find out that this y1 would also be equal to L over 4. Then when we come and consider our second area, A2 would be given by a half times our base, which is L over 2, then times our height. Our height would be given by a half QL squared minus 1 over 8 QL squared, which gives us 3 over 8 QL squared. This gives us 3 over 32 QL cubed. Then we come and find the y2 by using this point, the center. Then you come and draw it downwards. This is y2. This one here was y1. This one here was y1. So from this point up to this point, it would be 1 over 3 what? 1 over 3 times L over 2. So that is 1 over 6. So if that is 1 over 6, so we take a half minus 1 over 6 and find this length this side, and then we use similar triangles to come and find the what? To come and find the height y2. So if we do that, we shall come and find that y2 would be equal to L over 3. And then lastly we come and calculate the area of the third shape. So this one here would be equal to now our third shape, we said it's a semicircle, so the area of a semicircle would be 2 over 3 BH. So our B would be equal to L over 2, and then our H. Now the semicircle, like this center part of it, the value of the moment is always given by 1 over 8 Q L squared, but then our L is equal to L over 2. So this becomes 1 over 96 Q L cubed. Therefore, yeah, like that. Then now we come and find our y3. So the y3 is just also at the center, a dotted line, and then we come and discover that it passes through exactly the quarter part of the whole of the beam, as in like a distance of L over 4. like this, so that is the same as that of the what? Of the rectangle. So it takes on the same value, that is L over 4. So after we've found all these, now we come and calculate our displacement. Yeah, okay, before we even we come to the displacement, let's try to check on the signs here. So when you look at our shape A1 and Y1, we see that they are on the same side, so therefore it takes on a positive, yeah. Then when you come to the second shape A2, they are all on the top side, yeah, isn't it? A2 and the shape of which where Y2 is taken, are all on the same side, so this is also positive. But now when you come to the Y3, we see that from this unit force diagram, it is evident that our shape is on top. But now when you come on this shape here, on the semicircle, we see that its baseline, this one here, how should I explain? Like we take the baseline to be okay. If I was to take this shape and superpose it to this very last bottom here, like we discover that this area here would be of this nature. Like if I was to superpose it on this very sector, I would be having my semicircle of that nature, like that, isn't it? So therefore, when I look at this shape, it would be down, but then this shape here where I take the Y2 would be up. So therefore, for such a shape, this baseline, that this imaginary line that we've added for the baseline, we take it to be as if it is the beam. So using that idea, we see that it's on the opposite side, therefore this becomes a negative sign. So therefore our displacement delta C would be given by 1 over EI times the summation of the area. So we shall be having A1 Y1 plus this would be A2 Y2, and then this becomes a minus A3 Y3. So when we work out this calculation here, we shall discover that we get our answer as 17 over 384 EI times QL power 4. Yeah, so basically that is how we work out these numbers using the shape multiplication method.